thank you all. Thank you all for coming. I'm very honored to be here today to try to tell you a little bit about the value of the moon. You might think that's kind of a strange title. What do I mean by the value of the moon? The moon has value in the sense that it is a target in space that is accessible to us and at the same time useful to us. And hopefully at the end of this talk, you'll have an appreciation for what I'm talking about. So let's start off by looking at some of the principal properties of the moon. And the first one to recognize is that the moon is close. It's 400,000 kilometers away. And it's in orbit around the Earth, which means that it's constantly accessible. You can go to the moon at any time. There's always a launch window open. That is not true for any other heavenly object. It's certainly not true for the asteroids. It's not true for Mars, where you only get launch windows every 26 months. The moon is always accessible and it's close. The closeness comes in terms of our initial return to it. It's a place from where, if we get into trouble, we can get back pretty quickly. So that's the primary value of the moon from one sense, is that it's close and accessible. But the moon is also interesting. It is a miniature laboratory of planetary science in that the processes that have shaped the rocky planets, impact, volcanism, tectonism, which is the deformation of solid crusts, and regolith formation, the erosion of the surface. All of those processes operate to 1 degree or more on all the rocky objects of the solar system. But more than a laboratory for studying these processes, the moon contains a record of the Earth-Moon history. It's in the same part of the solar system as the Earth. So the impact history of the moon is also the impact history of the Earth. And if we can recover and read that, we can learn new things about the earliest periods of the Earth for which that record is gone because of the Earth's dynamic processes. Finally, and most importantly, it's useful. And it's useful in the following sense. The resources of the moon allow us to create new capabilities in space. And as I go through this, you'll kind of see that this largely revolves around the recovery, the discovery, the recovery, and the extraction of water from lunar surface materials, because water is a very useful substance to have in space. So let's look to start off with at the lunar poles. Why is the moon useful? Well, it's very simple. Amazingly enough, it's a simple property of the obliquity of the moon's spin axis. The moon's spin axis is inclined 1.5 degrees from the perpendicular to the ecliptic plane, which means effectively that at the poles, the sun is always on the horizon. Now, the sun is 0.5 degree in angular width. So over the course of a 608-hour lunar day, as the moon rotates on its axis, an observer at the poles would see the sun hover either slightly above or slightly below the horizon. Now, if you're on a peak at the pole, you might see the sun all the time. But conversely, if you're in a hole, like the floor of a crater, you might never see the sun. And this simple property creates a microenvironment of the lunar poles, one which in the last 10 years or so we've discovered actually has some really useful properties. Now, I've used this phrase before. I first used it in 1996 when we were talking about the Clementine radar result. I think the poles of the moon are the most valuable piece of real estate in the solar system because they enable permanent off-planet residence by humans on another world. And that's related to these two properties. First, the idea that you have areas of near permanent sunlight. The map on the left shows this. The dark blue areas are in permanent darkness. The bright areas that you see on crater rims, yellow and red, are areas where you have sunlight for more than 85% of the lunar day. So that property alone allows you to generate electrical power all the time. You don't have to worry about the 14 days of daylight and the 14 days of nighttime that the moon undergoes at its equatorial and mid-latitude regions. And secondly, these dark areas have some really interesting properties. They're dark, which means they never get solar incidence, which means that the only heat they get is from the 3 Kelvin background radiation of space and from the internal heat of the moon itself, which is very low because the moon's a very small object. So in consequence, you find in these dark areas deposits of water ice. And the story of us finding this water ice and how we determined it's there and what its properties are is kind of interesting. I'll go through that as I talk about this because it's been a long, kind of a strange trail we've followed to get here. And it's interesting that we still don't know the key elements that we need to know in order for this to really work as from a complete end-to-end viewpoint. So let's talk a little bit about the two poles. They're actually both in highland terrain. If you look at the moon, you see dark, flat, smooth areas, the maria, which are the seas of the moon. They're basically floods of basaltic lava. The rugged cratered highlands is part of the original crust of the moon. It's composed of material that's thrown out by giant craters and basins that have resurfaced the entire surface of the moon and created a cratered, rough surface. Both North and South Pole are in the highlands of the moon. So if you're looking for lava tubes, this is not the place to go because you're not going to find them. But fortunately, the moon cooperates with us in that they have a lot of these holes. If you want to live underground, and that's good from a lot of perspectives because underground has a nice constant thermal environment, you're protected from radiation, from solar particles, and it doesn't undergo these temperature extremes of night and day. And you can do that at the moon simply by placing your habitat in a small shallow crater and then backfilling the crater with soil. So you can bury your habitat quite easily and create an underground dwelling. Now I mentioned the solar illumination. These two maps concentrate on the 1.5 degrees around each pole, north and south. And what you see on these images is the black represents permanent darkness and the white represents areas in high amounts of sunlight. And you'll see that high amounts of sunlight tends to follow crater rims, which makes sense because crater rims are the highest peaks in these areas. And especially the South Pole has a lot of relief simply because it's on the floor of the biggest impact basin in the solar system, the South Pole Aitken Basin. And so these particular peaks near the South Pole have areas where you see the sun for more than 90% of the lunar day. And what's more, the times when they're in darkness is not continuous. It's based on the local topography. It's not a result of any variation in the orientation of the spin axis. So these areas are non-contiguous and they occur of variable duration. The longest are on the order of a few tens of hours. The shortest are a few hours. And those are time periods easily bridgeable with alternatives to solar power generation. The other thing that we found through a variety of missions over the last 10 years is that there is a lot of water on the moon. And one of the most interesting discoveries came from the Indian mission Chandrayaan. This particular map shows the front side of the moon. It's a spectral image showing the strength of the 3-micron absorption band, which on the moon is caused by the presence of H2O or hydroxyl, OH molecules. And what you see is that it starts at high latitudes at both poles with this blue color, and it gradually becomes deeper blue all the way to purple as it gets near the pole itself. Fundamentally, this is a measure of the strength of the 3-micron absorption. The strongest and highest concentrations of water and hydroxyl occur at the highest latitudes. And this is probably a function of the mean surface temperature. As you get to higher and higher latitudes, the average surface temperature in these latitudes is much lower than it is at mid-latitudes or the equator. So some process is generating water and hydroxyl, and it's migrating. It's basically moving from the lower latitudes toward the higher latitudes. In addition, we have a variety of other remote sensing data that tell us that the dark areas contain something really interesting. These maps show the shading, the illumination at the poles, the measurement of the data from the neutron spectrometer from Lunar Prospector, and finally, there's something called the circular polarization ratio from the imaging radar that was carried both aboard Chandrayaan and from the LRO mission. And what you see is that first, that these neutron high areas of high concentration of the element hydrogen occur in areas of permanent shadow, which is to be expected. If this is caused by water ice, then you'd expect to see high hydrogen in the areas where there's a lot of shadow. The other thing you see is that it's not a perfect correlation, but the anomalous craters that you see with high radar same-sense reflectivity tend to correspond to areas where we've already identified anomalies based on hydrogen. All of these measurements together are suggestive, they're not definitive. So what we tried to do was to figure out a way to directly sample this, to directly go down to the surface and see what is actually causing this unusual signal that we see around the poles of the moon. Now this particular mission, the LCROSS mission, was actually an add-on to the launch of Lunar Reconnaissance Orbiter back in 2009, I'm sorry. And effectively what we did was to take the upper stage of the LRO launch vehicle, which was a Centaur, and crash it into the moon, and then observe the plume, the ejecta plume that was thrown out of the moon from that crash with a following satellite. In addition, it was also observed by the orbiting LRO spacecraft, which had entered lunar orbit a few months before, and by ground-based telescopes. And we aimed specifically for the crater Cabeus, which is near the south pole of the moon. Cabeus was interesting because when we looked at the neutron data, it had the strongest absorption showing of epithermal neutrons, which indicated there was a lot of hydrogen present there. It formed a crater about 80 meters across, and that crater ejected through a plume that went up several tens of kilometers above the moon. Now, the following satellite observed this plume. So it's not only observing the vapor that's in that plume, it's observing particles of material thrown up into the plume as well. And this is the result. What they got was a spectral absorption curve that looks like this. The indications are that water vapor and water ice particles in the ejecta plume are in the order of 7.5, plus or minus 5 weight percent. So between 2.5 to 10 weight percent, 12 weight percent, water is present in this particular target. Now keep in mind, this is only for about the upper 4 or 5 meters of the surface. We don't really know how much is present at depth. We've recently done some bistatic measurements of Cabeus to suggest there's significant amounts of ground ice present within a few meters of the surface. So why is water so important? I've kind of indicated that it's a particularly useful substance. In space, it's sort of the universal solvent. It answers so many questions and so many needs. The obvious one is it's a life support consumable. You can drink it, you can use it to reconstitute your food, you need it for sanitation. It's a critical need on space station. It'll be a critical need for any humans that go anywhere in space. In addition, you can also crack it into its component gases and breathe the oxygen. So air and water together can be generated from water that you get from space. In addition, it also serves human needs by acting as a radiation shield. If you jacket your habitat or your deep space spacecraft in a bladder full of water, you'll protect yourself not only from galactic cosmic rays, but also from solar particle events, coronal mass ejections. Use in a fuel cell. You can take hydrogen and oxygen and combine them in a fuel cell to generate electricity. And then when the sun's out, that leaves water as a byproduct. You can collect that water and then crack it into its component gases with solar array-generated electricity when the sun is out. So it's a medium to store energy. And I mentioned earlier, we had these short periods of the permanently illuminated poles where you don't have solar incidence. You can fill those gaps with fuel cells that use the water that you've produced from electrical power when the sun is out. And finally, and most importantly, hydrogen and oxygen together are the most powerful chemical rocket propellant we know of. Liquid hydrogen and liquid oxygen power the shuttle main engines. They will power the spacecraft rocket engines of the future. So effectively, finding large amounts of water on the moon makes the moon a logistics depot in space. And why is that important? Because fundamentally, right now, everything we take into space, we have to lift out of the deepest gravity well in the inner solar system. And that's the 13.5 kilometer per second gravity well of the Earth. If you're on the moon, that's only a 2.6 kilometer per second escape velocity. It's much easier to lift stuff out of the moon's gravity well than it is to lift out of the Earth's. So we're not proposing to go to the moon to build rockets to launch to Mars or to launch to Jupiter, but the moon's water can be used to fuel those rockets because most of the rockets that go into space are mostly propellant anyway. And this, my friend Don Pettit calls this the tyranny of the rocket equation. The rocket equation dictates that more than 90% of the mass of your vehicle is fuel. So effectively get your fuel, your low information density material, from a place in space rather than lifting it out of the deep gravity well of the Earth. So what might a transportation system that can access the moon routinely look like? Well, we might have, rather than thinking about an Apollo architecture where you have a giant rocket, you have a lunar module, you have a command module that comes back and is a small piece, let's think differently. Let's think about permanent assets that are based in space, that stay in space and that are reused rather than discarded. Let's think about making small journeys between these various intermediate steps and then using the same pieces to do that multiple times. All of this being fueled by propellant that you produce on the moon. So one key element of this is having a fuel depot in low Earth orbit, which allows you to basically bring people and machines up from LEO. They go to the low Earth orbit fuel depot to transfer to a cislunar stage, which then takes the vehicles, the people and cargo out to the moon. And effectively, this is shaped with a disk because it has an aerobrake. It uses a rocket engine to propel itself out of low Earth orbit, but it uses the aerobrake to come back to Earth orbit, saving fuel for their return trip. In addition, the cislunar transfer vehicle can also access different satellites at various points in cislunar space to do a variety of different repairs and refurbishments and maintenance on them. You might expand satellite servicing into a much greater and more robust activity where you have both people and robotic machines surfacing satellites in geosynchronous orbit. Right now, civilization is critically dependent on space assets for a lot of things, for weather forecasting, for GPS, for national surveillance, for remote sensing. All of these different functions depend on satellite assets, all of which are situated in the volume of space between Earth and Moon. Now, right now, those satellites are built with a custom template. They're launched, and they're discarded when they wear out. They're not refurbished, they're not maintained, they're not rebuilt. What if instead you could actually maintain these things and build big distributed system using people and machines? Construction of the ISS showed us we know how to do that. What I'm suggesting is we can use that paradigm and apply it to all of the space assets in cislunar, not just the International Space Station. The Lagrangian points are interesting because they're places that stay in the same relative position relative to Earth and Moon all the time. And you've heard a lot about L4 and L5, which are the stable Lagrangian points. But it turns out for a cislunar transportation system, L1 and L2 are actually more useful. So you might have a depot and a transfer node in L1, which is 60,000 kilometers above the center of the near side of the Moon. L2 is 60,000 kilometers above the center of the far side. And this might be a place where the cislunar transfer vehicle drops its cargo and people who then transfer to a lunar lander. The lunar lander can then go down and either burn into low lunar orbit to get into the proper position for some site you want to access, or it can go directly to the Moon if it has the proper amount of fuel, which is about 2.6 kilometers per second of delta V. The lander can be will be both heavy robotic landers and human landers. And they're not going to look like the lunar module. They're not necessarily built around life support for the crew. They're built to carry cargo and maybe habitat modules with people down to the surface for ultimate use on the lunar surface. So initially, what we want to do is to go to the Moon, process its resources to see how difficult it is, and that can all be done with existing vehicles. The commercial launch vehicles and recognized extensions of them can land the initial 1 to 2 metric ton class vehicles that can do the initial work on the Moon. Ultimately, when we have large heavy lift vehicles like the SLS come online, we can launch much bigger pieces of equipment or collections of pieces of equipment at the same time. And ultimately, what you want to do is to come up with a system that allows you to process and generate significant quantities of water and propellant on the Moon. Largely, this will be automated. It will be done by machines, but you need people there to both oversee it and to service things when they go bad. You can use this system to do things that, for example, you can't right now. Suppose in the future that this is actually a proposal to put a telescope at Earth, Moon, L2, behind the far side of the Moon. The diagram is sort of based on the James Webb, and right now the James Webb cannot be serviced. Human crews cannot get to it, and what's more, the satellite is not built to be serviced by people. It's not like the Hubble. On the other hand, the next time we launch a space telescope like this station at L2, if we can get to L2 and service it, we can basically give it unlimited lifetime and upgrade it and maintain it, just like we did with the Hubble Space Telescope. So, how do we go about this? How do we go about getting on the Moon and doing all the things I've described? I used to call this how to go to the Moon in 5 easy steps, but I've changed it now to phases, because phase steps implies that you take one and then you take the other. They're sequential. Phases can be overlapping, and these things are probably overlapping. So phase 1 is to prospect and demonstrate. You want to prospect because although we know there's water at the poles, we know where the dark areas are, we know where the sunlit peaks are, you want to be able to know exactly how much water is there, what its physical state is, what is it combined with. The water ice is clathrated with other materials. We saw in the L-Cross plume that there's at least methane, there's ammonia, there's carbon monoxide. All of these other volatiles are potentially useful for a variety of different things. So we want to characterize what's there, we want to characterize what its concentration is, and how to get at it, and can it be accessed. And if it can be, can you do anything with it? In other words, we want to figure out how to extract it efficiently, how to separate the water from whatever it's contained in, and how to purify it for the various uses. Finally, when you've got pure water, you want to then electrolyze it into its component gases and then cryogenically freeze them. Now, that's not going to be as difficult and as power intensive as it sounds, simply because we have the dark areas of the Moon to help us on this. Some of the dark areas are as cold as 25 Kelvin, so they're actually colder than the surface of Pluto. So it's going to be much easier to make liquid hydrogen there than it would be at the surface of the Moon, at the equator of the Moon, where it might get up to 100 C during the lunar noon. So robots in this phase 1 prospect and demo. They prospect where the water is, what its physical state is, and then they demonstrate how to extract it and how efficient the various processes are. Phase 2, you start landing bigger robotic assets. bigger robots to do mining, processing, and storage of the product. So effectively, you're doing these robots are not autonomous. They're all teleoperated by operators on the Earth. This way you get a core of people who have expertise with actually being on the moon without actually sending them on the moon. You're effectively using them to use the robots to mine the moon and process the water. Once you have the water, it's easy to store. All you have to do is put it in a dark hole trap on the moon. It'll stay there forever. It will not sublime away. It'll be safe until people come there and use it. So the phase 2 is like phase 1, only now you know where the water is. Now you're going there and you're actually starting to make water. And once you've started to build up a stockpile of that product, you move on to phase 3, which is in placing the lunar outpost. And effectively, this is another thing that we can do before people arrive. You can use teleoperated robots to assemble the lunar outpost. So not only will they use techniques like 3D printing to make various structures, but they'll also do significant amounts of earth moving. You want to make berms to protect habitats and various forms of surface equipment from flying dust. You want to emplace your habitats. You want to bury them with regolith to protect them from radiation. You want to install power systems and thermal control systems. All this stuff can be done with robots under the control of people on Earth assembling the lunar outpost. Phase 4, people return to the moon. And I often get the question, well, why do you send people? If the robots can do all this, why send people at all? Well, I contend that people have unique abilities they bring. People can recognize the significant, and they can distinguish the significant from the trivial. My field is geology, and when I'm in the field, it's not a matter of just picking up rocks. It's a matter of recognizing what the most significant rocks are, what they tell us, what their story is in terms of the chain of events that brought the landscape I'm looking at into existence. I want to understand that at all levels of detail. And to do that, I need to be there. I need to walk outcrops. I need to pick samples. I need to revisit places that I've been to before. People can do this. People can interact with the environment quickly and easily, much more simply than robots can. But more than that, people actually are able to bring their own expert knowledge and background to bear on problems on the moon. So in terms of innovating solutions and coming up with ideas that a machine couldn't, I think people are needed, and I think people will want to go in any event. And once you've built the outpost, you're going to need people there to do all these things that I've described. And in phase 4, you're going to have a gradual buildup of people as time goes on. Once the robots have built the outpost, people are going to come and do all the things that people want to do. People may want to build a radio astronomy observatory on the far side of the moon. You're going to have geologists who want to explore different parts of the moon. You're going to have life scientists who want to understand what the effects of reduced gravity are on human tissue and adaptability. All of these things can be done at a human-tended outpost. And finally, phase 5 and beyond is opening up space. We're using the propellant that you're making from lunar water to fuel a cislunar transportation system. And that allows people and machines to go anywhere at any time. And that's really, I contend, our fundamental goal of people in space, is to go wherever we want, for as long as we want, for whatever capability, bring whatever capability we need to solve whatever problem we want to look at. That's what we're trying to do in space. And we're not want to confine ourselves only to the moon or only to Mars or only to an asteroid. We want to go everywhere. We want to do everything. And the way to do that is to start building an infrastructure that's based in space and that uses the material and energy resources of space. So I think that if we were to do this, you would make the moon part of man's world. You're effectively making cislunar space into the first theater of operations that's as common as the oceans are today. And I've kind of come up with a cartoon of the things that could happen, all of these different activities that you see, from low Earth orbit with the ISS and propellant depots that are there, to satellite service that can occur anywhere from LEO all the way to GEO, to transport nodes and various scientific instruments at the Lagrange points, and then finally to the use of lunar resources on the surface of the moon and lunar exploration. All of these activities are propelled by propellant that you manufactured from lunar materials. So effectively, you've taken what you found in space and you've used that to create new capability. So the moon is close, interesting, and useful, yes. But more than that, it has value because it enables us to create the system that we want, the system that will allow us to go anywhere in space to do whatever we want for as long as we want. So with that, I will stop and answer your questions. Thank you very much.